Millennial Power Million. Good morning, Namaskar. This is Engineer Suraj Singh. It's until Saturday, 4:32 a.m. Little late today due to some reason. Still signals probably are working, I'm sure. That's why I'm talking. And it is Namaskar, मैं सूरज सिंह सिविल इंजीनियर भारतीय से बोल रहा हूँ. आज अप्रैल 16 2022 शनिवार 4:32 सुबह के. Or you can say title of talk is same as it was yesterday, and it was starting real quality requirement, ending with what we do, and in between our coordination engineering, only way, projects, works, design, contracts, reliable engineers, power of communication, concrete specifications, civil engineering, safety, health, environment, methods, disputed claims, etc., etc. And let me go to you before my profile, and this my profile. Here is you can say Suraj underscore engineer at yahoo.co.uk. You can write it Suraj underscore engineer at yahoo.co.uk. I am chartered engineer, I am professional engineer, I am an arbitration engineer, I am FI like that. And this is my certification of professional engineer international, and this is my arbitration certificate, arbitration engineer certificate that I got on April 4th this year, 2033. This is chartered engineer certificate, which has been very, very long. You can say more than decades, many decades, and this is quality file. I close chartered engineer certificate, and of course I close arbitration for this arbitration certificate as well. And let me talk on coordination file, and I open also cement concrete file. Concrete file we'll discuss in combination with coordination and quality. Concrete file as well as you can say quality, which is root of everything, which is source of everything that we can say, which is power of everything. Quality I consider as power in this world. If we think ourselves we are quality people, we must prove that we are. I'm writing on behalf of the whole world, but this particularly Bharat India speaks about. I'm talking of my country because I think in my country quality is at very, very low level. It should be avoided. Quality in my country, Bharat India, exists at very low level, professionally, business-wise, and we least bother. I didn't find people who are very serious in talking about quality. Even institutions which are responsible for this do not speak a lot on this. It's unfortunate, and not only in ours, but also I see other countries do same. There is no major difference, but here there is no hunger for quality. That's I'm finding there is no hunger of quality anywhere. I mean, quality is not made an aim, an objective. It should be. It should be made an aim, an objective. I don't reason behind that why it's like that, but it happens. Quality is not. When I say quality, this means the real quality, not just papers, not just statements. Production, manufacturing, construction, all should have quality systems and inbuilt quality. We cannot simply say we cannot simply say we got quality only using certain documents. No, product must give quality. It may be whatever kind of product. It may be some object, it may be service, it may be governance, it may be management, it should be production, it should be product delivery, it should be maintenance, it should be service, it should be individual life. Whatever is least expected, at least that should be given. But it doesn't happen, unfortunately. We sleep, and particularly in this modern world, which is full of digitization, which is full of money power, people have left behind quality. Quality, in fact, not only left behind, but it has been disappearing. If I compare my time, now I am 68 years, if I compare my time when I started my career in 1975 And further, particularly in 1981, when I joined overseas jobs in Middle East and Gulf, and when I compared my engineering works which I did in this country, Bharat, India, and those which I did in Iraq or Gulf, I could actually learn there practical aspects of engineering construction and engineering itself. I could learn a lot about quality, though there was no system as such in those days. Quality name in systems did not exist. No computers exist, only calculators. Well, I think that was good lesson for engineers like me and for generations like me in those days when we had to do everything manually from scratch to finishing. Every item was done manually, and that was greatness of profession to learn practically. Time changed, quality lifted itself. But since quality and computers entered, though computers entered earlier than quality, that's a fact. But computer is a source for advancement. Computer cannot work for itself. Whatever we feed in that, it will work like that. Same thing is quality. Whatever we decide, whatever we consider, we have to achieve this, only that we can achieve. It depends on experience, it depends on theoretical knowledge, it depends on your observation, it depends on, you can say, experience of performance. When you have products of very small life, for example, some product works for 2 years, some works for 1 year, some works for 5 years. In those products, performance can be understood very fast because you have to dispense with and indispense with both all these products. We can know how does it work when the question comes to long duration product like construction products, concrete product, and many others, where you have to use those products for long time. It is very difficult to know immediately how shall you feel, how shall you experience about that. And that's why, experience of quality is very important. It takes time, you have to think on others and we have to think on everything like that. Only then we can say we can do something, or we can say we can do something like that. That something like that is very important point. And we have, just like I'm showing a file of concrete, which is very significant. And we have many references because this specifications means quality itself. The specifications means quality itself, and we can't say otherwise. And therefore, I am talking in parallel to concrete because concrete is such a material which is used in abundance in construction worlds. I can say whatever construction we do, whatever development works we carry out, concrete is associated everywhere. Even if you have machine, you install machine, you require certain plinth for machine, you require certain foundation. In major machines, for example, a major compressor machine, you have to install on some plants, very big one, or you have to install some equipment, means you require some foundation for that, and that foundation means generally it is concrete. Buildings means foundations are concrete, structures are concrete. Of course, even if it is structural steel, you require certain foundation, and that's why we say machine may finish in 20 years, 30 years, 15 or 20, 12 years, 10 years, but you can say foundation still exists. Same thing for buildings, it stays for many decades to come. We have to differentiate between what level of quality do we need, we require, and we have to not only do what level, means it should be performable in when actions of winds apply, when seismic actions apply, when vibrations apply, all those must be registered by that foundation. And that's what the design and quality criteria, and design and quality criteria are considered in conjunction with coordination, means engineering coordination, technical coordination, practical coordination. All those must be understood. Each plus and minus points must be known, and that's what coordination engineering I talk of. I don't have to go further. Just for purpose of explanation, I am saying That reliable coordination, reliable means it should be workable, it should be safe, it should suit purpose, and also you can say it should be durable. We can say, first we say reliable means it should be safe, it should be functional, it should be durable, and it should give every possible result, every possible use which you expect of in coordination. Coordination cannot be put in isolation, it's a part of job. Without coordination, job cannot be done, whatever job we do. In engineering or otherwise, even in personal life, coordination is very important. Individual coordination is very important. And documentary coordination is very important. And if you are in designs, then codal coordination and formula coordination. Likewise, in concrete, you can say material coordination. So much is required for that. We cannot just keep it. We go to concrete now. For example, we are talking here hot weather concrete. Before that, we talked of concrete that is cold weather, and it says formwork and shoring, and it's talking about yesterday at the criteria for curing periods to achieve specified compressive distance. We talked of that in this case, and now we are talking of formwork and shoring. Formwork and shoring, you know what is formwork? Formwork is very simple management. It's very simple system which gives us support for concrete to strengthen, the concrete to set. And its shoring is also required. Formwork should have good heating retention. Formwork should have good heat retention. That is first criteria here. Heat retention. Lateral pressure acting on formwork shall be determined. Lateral pressure acting on formwork shall be determined taking concrete temperature into consideration with reference to whatever section. Shoring shall be placed firmly on ground. Shoring shall be placed firmly on ground without any deformation on account of frost heaving of ground or thawing of frozen ground. Removal of formwork shall be carried out in a manner that temperature of concrete does not drop rapidly. Temperature of concrete does not drop rapidly. So these are very important points here. It means good heat retention, lateral pressure acting on formwork, which we have to determine depending on temperature into account, and also shoring be placed firmly on ground without any deformation or settlement, or you can say whatever removal of formwork shall be carried out in a manner the temperature of concrete does not drop rapidly. Now compare with steel forms, we have wooden forms. Compare with steel forms, wooden forms have lower thermal conductivity, and therefore provide better heat retention. Here is a comparison. Means steel is good conductor of heat, but wooden formworks are not that good conductor, you can say. Lower thermal conductivity applies to them, and that's why we say heat retention is more important in case of wooden formwork. Means if you use plywood or use timber planks. If concrete section is thick, it is efficient to take advantage of effect of temperature rise due to heat of hydration of cement when volume is more. Even when concrete section is thin, it may be possible to provide insulation without heat supply by combined use of foamed resin and shuttering. When steel forms are used, it is necessary to pay sufficient attention to insulation since steel is readily influenced by rapid change in ambient air temperature. This is a very technical point we have to consider in our approach here. What technical is important here. This point is very easy to understand when we say here. Let me read it again for you so that it's clear. It says, compared with steel forms. Compared with steel forms, wooden forms have lower thermal conductivity and therefore provide better heat retention. If concrete section is thick, it is efficient to take advantage of effect of temperature rise due to heat of hydration of cement. Even when concrete section is thin, it may be possible to provide insulation. If it says even when concrete section is thin, it may be possible to provide insulation without a heat supply by combined use of foamed resin and shuttering. When steel forms are used, it is necessary to pay sufficient attention to insulation. When steel forms are used, it is necessary to pay sufficient attention to insulation since steel is readily influenced by rapid change in the ambient temperature, air temperature. As concrete temperature falls, lateral pressure acting on formwork tends to increase. As concrete temperature falls, lateral pressure acting on formwork tends to increase. It, if temperature falls, it says means cold. So setting is delayed. Little pressure acting on formwork tends to increase. Reason being that when temperature is low, setting is very delayed, and you can say little pressure keeps on acting. It is necessary, therefore, to determine lateral pressure values to be used in formwork design, taking this tendency into consideration. When shoring is directly based on ground, proper location, configuration, and dimensions of structure may not be secure due to frost, heaving, or thawing of ground. In some cases, shoring may collapse. Therefore, when above mentioned is predicted, it shall prevent frost heaving or to avoid adverse effects of displacement caused by frost heaving or thawing by adopting measures such as pile foundation. Therefore, when above mentioned is predicted, it shall prevent frost heaving or to avoid adverse effects of displacement caused by frost heaving or thawing by adopting measures such as pile foundation. Inner temperature of structure. Inner temperature of structure with a thick section rises considerably due to heat of hydration. Temperature differences may develop when concrete is rapidly cooled down after shuttering, removal, and cracking may occur. Therefore, it's desirable to remove shuttering after minimizing temperature differences by adjusting temperature within enclosures or, or to retain shuttering until concrete surface not be subject to rapid cooling even after specified strength for removal has developed. For example, maximum allowance on a temperature drop within 24 hours after end of curing is 22 to 28 degrees Celsius. Maximum allowance on a temperature drop within 24 hours after end of curing is 22 to 28 degrees Celsius for a thin section, 17 for a thick section. Now we are going to talk about hot weather concrete. It was cold weather, thus continuation it is hot weather concrete. Hot weather, which is very important factor where in summer and particularly where temperatures are high, particularly in Gulf countries, in hot, in our country, Bharat, India, also in many parts of our country, hot for southern parts as well as in north, and also many countries you can say where temperature is an issue during daytime as well as night time, when mean daily temperature is likely to exceed 25 degrees. 25 degrees, I am talking of mean daily temperature that is likely to exceed 25 degrees Celsius. Provision of hot weather concreting must apply, should apply. 25 is not, I can say, very wonderful, but just let's assume 25 is say day temperature is 40 and early morning now say it is more than 24 or something, so it is 30 or like that, so it exceeds 25 degrees even up to 30 say in daytime and maybe 15 or 10 morning. There is a difference of 20, but 40 25, so it's like to exceed 25 means average temperature, daily temperature, mean daily temperature is likely to exceed 25 degrees. We apply hot weather concreting. In hot weather concreting, appropriate measures shall be adopted during transportation of concrete within site, placing and curing of concrete so that quality of concrete is not impaired due to high temperature. It is quite difficult to accurately define in which period of year hot weather concrete should be applied. It is desirable, however, to prepare for hot weather concrete when mean daily temperature exceeds 25 degrees Celsius, because characters of hot weather concrete become remarkable if temperature at placing time exceeds 30 degrees Celsius. It says because we have to consider not to exceed 25 degrees, when mean temperature exceeds 25 degrees, because characters of hot weather concreting becomes remarkable if temperature at placing time exceeds 30 degrees Celsius. Measures to be taken in connection with hot weather concreting should be implemented well in advance. High atmospheric temperature results in high concrete temperature and large slump loss during transportation as well as loss of entrained air. High temperatures also increase risk of cold joint development Cracking due to rapid evaporation of water on concrete surface. Thermal cracking, therefore, in order to minimize concrete temperature during and after placing, special care should be given to handling materials, mixing, transporting, placing, and curing concrete. Therefore, in order to minimize concrete temperature during and after placing, special care should be given to handling materials, mixing materials, transporting materials, placing and curing of concrete. All this must be cared for in order to minimize concrete temperature. It is also desirable that a construction plan be drawn up and construction work be controlled appropriately in due consideration of fact that a higher than normal temperature environment work efficiency tends to decline and workers are susceptible to heat stroke. We have to care about workers, we have to care about efficiency of work. And that's very important point, that it's difficult to do concrete in hot temperature. Again, I read, it is also desirable that construction plan or method statement, you can say, be drawn up and construction of work be controlled appropriately in due consideration of fact that in higher than normal temperature environment, work efficiency tends to decline and workers are susceptible to heat stroke. Now we talk of some materials when required concrete temperature cannot be attained. A method for lowering temperature of materials shall be determined and its effectiveness verified in advance. It is standard requirement. It is a standard requirement that air entraining water reducing agent, air entraining water reducing agents, and super plasticizers should be used or used should be retarder type admixture conform. It is also standard requirement that air entraining high range water reducing agent used should conform to specification. Well, temperature of cement upon delivery. Temperature of cement upon delivery may be quite high temperature. Temperature of cement upon delivery may be quite high depending on shipping conditions from factory. Although temperature of cement does not severely affect temperature of concrete, temperature of cement does not. Severely affect temperature of concrete in general, plus minus 1 degree Celsius in concrete temperature. Temperature of cement upon delivery may be quite high temperature, and depending on shipping conditions from factory. Although temperature of cement does not severely affect temperature of concrete, in general plus minus 1 degree Celsius in concrete temperature. Use of high temperature cement under hot working conditions, hot weather conditions. Use of high temperature cement under hot weather conditions is unfavorable as it raises temperature of concrete. Temperature of aggregates affect temperature of concrete greatly. In general, plus minus 2 degrees Celsius, change in aggregate temperature corresponds to plus minus 1 degree Celsius in concrete temperature. Therefore, aggregates, use of aggregates exposed to sunlight for an extended time period may produce a concrete temperature over 40 degrees Celsius. This shall cause an increase in unit water content, an increased rate of slump loss during transporting, and an increased rate of setting after concrete placement. Thus, aggregates should be kept away from direct sunlight using adequate facilities or kept in an appropriate condition by watering them. In general, purpose of this method of watering over coarse aggregate is to lower temperature by means of water evaporation. Method can be made even more effective by direct cooling coarse aggregate by use of cold water. Method of lowering temperature of aggregate by use of liquid nitrogen is used in some cases. Lowering temperature of aggregate by use of liquid nitrogen is used in some cases. Because of its latent hydraulic property, ground granulated blast furnace slag may consolidate in aggregate. It says because of its latent hydraulic property, ground granulated blast furnace slag may consolidate in aggregate storage facilities or storage bins during periods when daily mean temperature is higher than 20 degrees Celsius, thereby making it difficult to remove from storage facilities or storage bins. During such periods, it is important to avoid long-term storage. So, method of lowering temperature of aggregate by use of liquid nitrogen is used in some cases. Because of its latent hydraulic property, ground granulated blast furnace slag may be consolidated or may consolidate in aggregate storage facilities or storage bins. During periods when daily mean temperature is higher than 20 degrees Celsius, thereby making it difficult to remove from storage facilities or storage bins. During such periods, it is important to avoid long-term storage. In order to ensure temperature of mixed concrete, in order to reduce temperature of mixed concrete, it is desirable that mixing water be as cool as possible. To reduce temperature of mixed concrete, it is desirable that mixing water be as cool as possible. In general, plus minus 4 degrees Celsius. Change in water temperature corresponds to plus minus 1 degrees Celsius in concrete temperature. It is necessary for water storage tanks and pipelines to keep water temperature low by means of adequate methods such as shading, painting, storage, silos, white, and so on. Use of ice is very effective means of reducing concrete temperature, though it is generally not easy to possess ice crushing facilities. When water reducing agents or air and draining water reducing agents are used, retarded type agents instead of standard type agents instead of standard type should be used. If retarded type admixtures are used with the aim to prevent cold joints, it is necessary to carefully consider how to use them and determine quantity to be used appropriately. Air entering high range water reducing agents substantially reduce water content. Air entering high range water reducing agents substantially reduce water content and cement content. Even in case of hot weather concreting, air entering high range water reducing agents Air entering high range water reducing agents substantially reduce water content and cement content even in case of hot weather concreting. Depending on type of admixtures, however, amount of decrease in slump over time may be large at high temperatures, regardless of type of chemical admixture to be used. However, amount of decrease in slump over this time may be large at high temperatures, regardless of type of chemical admixture to be used. Therefore, it is important to select chemical admixtures that make it possible to maintain required minimum slump until planned time of completion of placement. Superplasticized concrete dramatically improves placeability. Superplasticized concrete dramatically improves placeability and quality of concrete. In general, however, slump of superplasticized concrete decreases considerably over time and this tendency may become particularly pronounced under hot weather. It is therefore desirable that either retarder type superplasticizers are used for hot weather concreting or retarder type water reducing agents, air entering water reducing agents, or other similar admixtures be used for base concrete. In mixed design of hot weather concreting, appropriate measures shall be taken so that water content and cement content do not become too high to an extent that required strength and workability can be attained. There exists a certain relationship between water content required to attain required workability and concrete temperature. Relationship exists between water content needed or required to attain required workability and concrete temperature just after mixing. In general, water content tends to increase by 2 to 5%. Water content tends to increase by 2 to 5% for every 10 degrees Celsius of temperature rise. In many cases, as concrete temperature rises, amount of change in slump and air content also increases. Consequently, when slump is adjusted by using such methods as adjusting surface moisture content of aggregate without taking control measures associated with hot weather concreting, concrete with higher water content and lower compressive strength than that of low temperature seasons might be placed. When water content water cement ratio is kept constant, and cement content is increased according to increase in water content with aim of attaining required compressive strength, conditions that are disadvantageous in preventing cracking due to high addition of cement results. It is necessary therefore to take appropriate measures after conducting prior studies to prevent water content and cement content from becoming excessively high to extent that required strength and workability can be obtained. To be more specific, it is necessary to determine amount of decrease in slump due to temperature rise and changes in slump over time and check whether required minimum slump can be attained until completion of placement. If water content needs be or requires to be increased substantially, it is necessary to take appropriate measures such as increasing uses of chemical admixtures, switching from air entering agents to air entering high range water reducing agents, or adding superplasticizers. We will be back to this, let's say mixing. Concrete temperature just after mixing shall be such that required temperature at time of placing can be obtained while taking into consideration the fact of weather conditions and time of transportation. It's also very interesting. Let me go back to study it further, and you may also read this mixed proportions are stocking. And in this case, you can see there's a certain relationship that exists between water content There is certain relationship axis between water content required to attain required workability and concrete temperature just after mixing. In general, water content tends to increase by 2 to 5% for every 10 degrees Celsius of temperature rise. Water content tends to increase by 2 to 5% for every 10 degrees Celsius of temperature rise. In many cases, as concrete temperature rises, amount of change in slump and air content also increases. Consequently, when slump is adjusted by using such methods as adjusting surface moisture content of aggregate without taking control measures associated with hot weather concreting, concrete with higher water content and lower compressive strength than that of low temperature seasons might be placed. When water cement ratio is kept constant and cement content is increased according to increase in water content with aim of attaining required compressive strength. Conditions that are disadvantageous in preventing cracking due to hydration of cement results. It is necessary, therefore, to take appropriate measures to prevent water content and cement content from becoming excessively high to extent that required strength and workability can be obtained. To be more specific, it is necessary to determine amount of decrease in slump due to temperature rise and changes in slump over time, and check whether required minimum slump can be attained until completion of placement. If water content needs be or requires to be increased substantially, it is necessary to take appropriate measures such as increasing uses of chemical admixtures, switching from air entraining agents to air entraining high range water reducing agents, or adding superplasticizers. Concrete temperature just after mixing shall be such that required temperature at time of placing can be obtained while taking into consideration the effect of weather conditions, time of transportation, etc. Lower temperature lower lower temperature of concrete materials is a good way to lower concrete temperature. Lowering temperature of concrete material is a good way to lower concrete temperature just after mixing. When, however, ice is used as part of mixing water, it is necessary to ascertain in advance that ice melts completely during mixing. There are also other methods such as method of injecting liquid nitrogen into mixer to lower concrete temperature directly. Temperature of mixers installed in a poorly ventilated plant. Temperature of mixers installed in a poorly ventilated plant with high indoor temperature due to solar radiations and heat generated by machinery might also be affected by heat supplied by pre-mixed concrete. Such mixers require to be cooled on an as needed basis. What it says, there are also other methods such as method of injecting liquid nitrogen into mixer to lower concrete temperature directly. Temperature of mixers installed in a poorly ventilated plant. Temperature of mixers installed in a poorly ventilated plant with high indoor temperature due to solar radiations and heat generated by machinery might also be affected by heat supplied by premixed concrete. Such mixers require to be cooled on an as required basis. In order to deduce temperature of fresh concrete from temperatures of materials with which concrete is made, equation which we shown here may be applied. However, the equation doesn't consider effect of heat of hydration and frictional heat due working during work mixing, so that actual concrete temperature under hot weather conditions may be about 1 degree higher than calculated temperature. Rise in concrete temperature during transportation is generally 2 to 4 degrees Celsius. Rise in concrete temperature during transportation is generally 2 to 4 degrees Celsius and 1 to 5 degrees Celsius for pre-cooled concrete. When calculating temperature increase during period between finish off mixing and finish off transportation and placing concrete, it may be to T2 is equal to T1 plus 0.15 T naught minus T1 T. This equation we discussed yesterday also. Transportation of concrete shall be carried out using means and methods so that concrete does not get dry or get heated during transportation. I'll be back in a couple of minutes. Meanwhile, you can read this because it's 5:15 and I have to be back in a couple of minutes. Sorry, gentlemen. Little worry. Concrete shall be transported using, now we're talking of concrete, we are talking of this. It is transportation of concrete shall be carried out using means and methods so the concrete doesn't dry or get heated during transportation. That's the important point. We don't want to heat additionally during transportation, and that's very important point. Concrete shall be transported using means and methods that minimize concrete temperature rise and drying of concrete. To do that, it is good practice to transport and place concrete as quickly as possible. For ready-mix concrete, it is required that process from mixing to unloading be completed in 1.5 hours. However, requires as a general rule that placement of hot weather concrete be completed in 1.5 hours at construction planning stage. That's why it's necessary to check whether concrete works requires to be carried out during a hot weather concrete period, and if concreting during such a period is expected, determine plant and transportation routes to be used. Estimate transportation time and take appropriate measures through consultation with plant so that transportation time can be made as short as possible. It's also important to plan and control vehicle operation so that truck agitators shall not keep waiting for a long time under hot weather. In connection with on-site transportation, it is necessary to study and find in advance methods for transporting and placing concrete as quickly as possible. Care shall be taken, however, that a higher transportation speed does not increase pipe pressure such that pumping becomes difficult or there is a delay in compaction. Finishing and curing. If concrete is transported by pumping, it is important, for example, to select locations so that pipes are not exposed directly to sunlight, to prevent pipe temperature from rising by covering pipes with wet cloth and to avoid interruption in order to prevent clogging due to decrease in slump. Read it again, it's very important. Concrete shall be transported using means and methods that minimize concrete temperature. We have to minimize temperature of concrete during transport. We don't have rise and drying of concrete. To do that, what we should do, it is good practice to transport concrete as quickly as possible and not more than 1.5 hours be consumed. For RMC, it is required that process from mixing to unloading be completed in 1.5 hours. It may require have a general rule that 1.5 hours in a hot weather condition. Placement of hot weather conditions, concrete will be complete in 1.5 hours. At construction planning stage, we have to consider this check how to do that. That's important. It's necessary to check whether construction work requires to be carried out during hot weather condition, hot weather concrete period, and if concreting during such a period is expected. We have to determine plant and transportation routes, and we have to discuss with plant person, site person, estimate transport time, and take appropriate measures. Through consultations with plant and transportation time can be made as short as possible. Important to plan and control vehicle operations where truck agitators shall not be kept waiting for long in hot weather. In connection with on-site transportation, it is necessary to study and find advanced methods for transporting and placing concrete quickly. Care shall be taken, however, so that high transportation speed does not increase pipe pressure such that pumping becomes difficult or they cause delay in compaction. If concrete is transported by pump, it is important, for example, to select locations on site so the pipes are not exposed directly to sunlight, to prevent pipe temperature from rising by covering pipes with wet cloth and to avoid interruption in order to prevent clogging due to slump. Placing. In areas where water absorbent, we have to place concrete. In areas where water absorption is expected. In areas where water absorption is expected, such as on ground or on formwork, water absorption is expected, such on ground or in formwork, areas shall be saturated with water prior to placing, and we generally do it on formwork, wooden formwork. Areas where water absorption is expected, such as on ground or formwork, areas shall be saturated with water prior to placing. Furthermore, when temperature of formwork or reinforcement is anticipated to rise substantially due to direct exposure to sunlight, appropriate measures such as water sprinkling or covering shall be taken. Concrete placing shall be completed as promptly as possible, and elapsed time from start of mixing to completion of placing should in general not exceed 1.5 hours. Temperature of concrete at time of placing shall not exceed 35 degrees Celsius. Furthermore, during construction, temperature of concrete and surrounding atmosphere shall be periodically measured and planned, or construction may be changed accordingly if necessary. When placing concrete in high temperature conditions, areas such as ground and formwork may easily dry out. This drying process affects flowability of concrete by absorbing concrete water. Therefore, necessary to saturate these portions with water before placing concrete. Temperature of formwork and reinforcing bars may rise substantially under direct exposure to sun. This results in quick setting of concrete and adversely affects quality of hardened concrete. Therefore, covering or sprinkling should be carried out to keep formwork and reinforcing bars at low temperature. It is necessary, however, to avoid excessive watering so that water is not left in formwork, and to observe conditions in formwork, and shall remove water left in formwork before placing concrete. Slump of hot weather concreting is highly susceptible to decrease over time. Consequently, concrete that has been left unplaced after being mixed may become difficult to place. If therefore a construction during a period when outdoor air temperature is higher than 25 degrees Celsius is expected, it is important to check on time dependent changeability of concrete in advance so that required minimum slump for placement defined can be met. In general, amount of decrease in slump is small for 1.5 hour after completion of mixing, and concrete can be placed without any problem during that period. Since such changes in quality tend to increase as air temperature rises, it is desirable that concrete be placed continuously and as quickly possible so as not to cause problems such as cold joints. Shows that allowable placement interval at an outside air temperature exceeds 25 degrees Celsius is 2 hours or less. It is desirable in case of hot weather concrete that shorter placement interval be specified in order to prevent occurrence of cold joints. Temperature of concrete placing time shall be as low as possible in order to prevent adverse effects. Upper limit of concrete temperature placing time has been determined to be lower than 35 degrees Celsius, possibly 32 degrees Celsius, based on various reasons. When temperature is lower than 30 degrees Celsius, adverse effect of temperature on concrete quality is relatively small under hot weather conditions. It has been observed that temperature of ready-mix concrete at point of discharge is between 30 to 33 degrees Celsius, and this temperature rises approximately 2 degrees Celsius during transportation of concrete to site. With currently available facilities, it is difficult for concrete plants to cool down concrete materials before mixing. Required concrete quality can be assured if concrete temperature is kept between 30 to 35 degrees Celsius by using a retarding agent or by rapid construction. When development of thermal cracks is anticipated, Verification of thermal cracking shall be carried out and concrete placing temperature determined. In hot weather conditions, concreting temperatures of materials and concrete should be measured. If predicted placing temperature or actual measured concrete temperature exceed plant temperature, construction plan shall be modified and appropriate construction methods selected based on measured temperatures of materials and concrete. Curing shall be started immediately after placing concrete so that concrete surface can be protected from drying. Appropriate measures shall be taken to protect concrete against direct sun and wind so that cracks due to rapid drying can be avoided. Surface of concrete placed under hot weather dries up quickly when exposed directly to sun or wind so that concrete becomes difficult to finish and potential for crack formation increases. Therefore, placed concrete should be cured as soon as possible so that surface does not dry out. Moist curing period shall be decided in accordance with table. In case wooden formwork is used, shall be kept in saturated condition during curing period since this formwork is likely to dry out. Moreover, exposed concrete surface should also be kept in saturated condition during curing period after formwork is removed. Especially in case of high temperature or low humidity, cracking is likely to occur due to rapid drying. Therefore, measures such as sprinkling or covering should be conducted in order to prevent surface from drying. What? Measures such as sprinkling or covering should be conducted in order to prevent surface from drying. For structures with wide surface areas like slabs, where sprinkling or covering is difficult, membrane curing may be applied in accordance with regulations stipulated. Membrane curing agent should be of type which absorbs only little thermal energy from direct sunlight. If cracking due to rapid drying of surface is recognized while concrete has not hardened after placing, revibrating or tamping should be conducted to eliminate cracking. Revibrating or tamping should be conducted to eliminate cracking when concrete has not hardened. Mass concrete. It's different, my dear friends. We are talking of something unusual, and before that I'll put my names again for you people. We are talking of quality and coordination, and now we are talking of concrete, and this is really wonderfully done. We have to recognize this fact of quality coordination. Now I'll go a little into mass concrete, but actually it is massive block concrete, to be very frank. In general, in cases where thermal stress due to heat generated by hydration of cement is problematic, where thermal stress due to heat generated by hydration of cement is problematic, concrete is regarded as massive block concrete, and measures to be taken carefully. Mass concrete verification concerning thermal stress and thermal cracking due to heat generated by hydration of cement shall be performed in advance in according to designs and general requirements. It shall be ascertained prior to commencement of construction that conditions assumed in design section of specification agree with actual construction conditions. If conditions assumed in design section do not agree with actual construction conditions, verification concerning thermal stress and thermal cracking due to heat generated by hydration of cement shall be performed prior to commencement of construction on basis of actual construction conditions. Prior to mass concrete construction, appropriate plans for concrete temperature control transportation, placement, curing, etc. shall be made so that effects of thermal crack control measures determined in advance can be achieved. Together with recent developments in advanced construction methods, there have been increasing demands for construction of large sized concrete structures. It has been frequently observed that thermal stress, which develops due to temperature variation during cement hydration process, causes thermal cracking of large sized concrete structures. These problems were once considered peculiar of concrete dams. The concrete dams or concrete structures with especially large sized members. However, harmful cracks are often recognized even in relatively small sized structures, depending on cement materials used and construction conditions. Therefore, concrete structures which face above mentioned problem. Therefore, concrete structures which face above mentioned problem of thermal stress due to heat of hydration shall be dealt with as mass concrete. But it says concrete structures which face above mentioned problem of thermal stress due to heat of hydration shall be dealt with as mass concrete, and consequently special considerations are necessary. Though it cannot be absolutely determined due to fluctuations of type of structure, materials used in construction conditions, size of member regarded as mass concrete is roughly considered to be not less than 80 to 100 centimeter in thickness for wide slab, or to be not less than 50 centimeter for walls, restrained at lower end. For concrete with rich mixed proportions, as in case of pre-stressed concrete structures, thin members may also be included in scope of this chapter. Depending on the restraining conditions, dam concrete is not stipulated in this chapter but in standard specific dam concrete. Crack controlling measures such as crack prevention or restriction of crack position and width should be taken at each stage of design, selection of materials, determination of mixed proportions and construction. Method for evaluating effectiveness of each crack controlling countermeasures. Countermeasure by quantitatively estimating influence of these measures on development of thermal crack at various stages has been almost established from recent researches. Verification for thermal crack in construction of mass concrete should be carried out in advance, verification methods, thermal stress and thermal crack caused by heat of hydration in mass concrete, where large amount of concrete is used continuously in order to satisfy desired concrete quality. It is especially important that all processes of production, supply, transportation and compaction of concrete are controlled completely based on construction plan. During construction of mass concrete structures, concrete may be delivered from several ready-mix concrete plants. As in general rule, cement and chemical admixture produced by some manufacturers, coarse and fine aggregates produced from same region should be used when possible. When materials differ for each ready-mix concrete plant, trial mix should be carried out in advance in order to confirm safeness of mixing before construction. When using chemical admixture, great attention is required because incompatibility between chemical admixture may be observed. Design section of this specification requires a general rule that verification be performed concerning initial cracking. Same chapter also requires that limit for crack width be set if cracking is to be prevented or permitted. Although design section assumes construction conditions for purpose of design studies, actual construction conditions such as weather conditions, air temperature, wind may change considerably prior to commencement of construction. Therefore, it must be checked whether pre-assumed conditions agree with actual construction conditions. If pre-assumed conditions have turned out to differ from actual construction condition and study results based on design section required to be modified, the studies must be conducted again before starting construction by method specified in design section of this specification on basis of actual construction conditions. In controlling thermal cracking during mass concrete construction, various measures for preventing cracking, controlling position, interval and width of cracks shall be carried out at construction stage in order to satisfy required function and performance of structure. In order to control thermal cracking, not only selection of cement type, materials and mixtures, mixed proportions, as well as adjustments of concrete placing temperature, but also selection of formwork dimension, lift height, joint position, placing time, interval, material and fabrication of formwork, as well as curing method should be considered thoroughly from production to construction stages. Depending on structure type, controlling crack position by crack inducing joints may be effective in some cases. Regarding these measures in making concrete and construction for controlling and preventing cracking, construction of mass concrete should be in general carried out in accordance with specifications, design in which requirements on material mix proportions, production and construction methods are prescribed in details based on prior examination related to thermal cracking. Other methods for controlling or preventing thermal cracking, such as using pipe cooling for damp concrete or large bridge piers, using expensive concrete or arranging reinforcing bars for crack control can be adopted. However, since these methods lead to cost rise, the technical and economical efficiencies should be evaluated. As now, general rule, cement and admixtures used in mass concrete should be one specified in design. If cement or admixtures mentioned in item are to be used, verification concerning thermal stresses and thermal cracks due to heat generated by hydration of cement shall be performed. We'll take up the remaining one. I think it's concrete and we have to be very careful about how to use it, how it's very important talk, and we should think again and again on these points we are doing, and only then we can reach somewhere, and that's the important point we have to consider. Now I'm going to close this talk for time being because we have to take care of some of us now. I'll do it again. We will repeat something here from this point of view, as this concrete is very important one for everyone. It's not just simple you can say we think or what we think. It's not that. It's actually it's something that should be taken care of correctly, and that's point we have to consider in our approach. Now you can say, because it is concrete, I just don't want to run only. I want to understand also. You should understand clearly what it is, how it is done, and how it is not done. So from that viewpoint, we may say, okay, that's right, what we understand in coordination engineering, we understand this, and also here in quality engineering, we understand this, and all that we have to know, to understand all this, and we will take now. Okay.